Hello, general chemistry students. As promised, here is that more in-depth video on Lewis acid-base theory. If you want just a little more of a general overview, you can check out the mud video I put up a few weeks ago about different theories of acidity. Lewis acid and base theory is the most versatile theory of acid and base chemistry that we have, and it has predictive power for a huge variety of reactions. But to understand where it comes from, we need to know a little more about the theory or the history of acids and base theory. The very first one really proposed was Arrhenius. He defined an acid as anything that, when placed in water, would create hydronium. And then a base was anything that would create hydroxide. Now, this was really more of a natural observation than a theory. He took previous observations and said, oh, well, this is what's practically going on, but it didn't have any predictive power. That's where Brønsted-Lowry theory came in. Brønsted and Lowry worked together and proposed that acids are species that can donate protons and bases can accept protons. Now, this is the theory we've been using for the last few weeks. This is a proper theory because it allows us to look at a structure and predict if it will act as an acid or a base. This is something that Arrhenius theory didn't let us do. But there's way more chemistry than just donating and accepting protons. What do we do about the cases that don't involve them? Take a look at this reaction. Solid calcium oxide reacts with gaseous sulfur dioxide to make solid calcium sulfite. This is the reaction that occurs inside the scrubbers that help remove air pollution from coal or natural gas combustion streams. Let's look at the mechanism. You have your oxide ion here. It has a lone pair of electrons that moves out and attacks the sulfur in the sulfur dioxide. That pushes some pi electrons onto one of the other oxygens. This is how you get from oxide and sulfur dioxide to that sulfite anion. But since there's no acidic protons involved, we can't use Brønsted-Lowry theory to talk about this reaction. What else could we use? This is where Gilbert Lewis comes into the picture. Gilbert Lewis was an extremely prominent scientist from about, the early 1900s to just after the mid-1900s, and he's one of the most amazing chemists we've ever had. He developed the theories of covalent bonds. He developed those Lewis structures that you guys learned to draw last semester. He developed valence bond theory. He did much important fundamental work in the thermodynamics of chemistry, which we just spent time learning about this semester. He named the photon, he isolated heavy water, and he proposed his Lewis acid-base theory. He's widely regarded as the father of modern organic chemistry, and his textbook about organic chemistry is still considered one of the most important books in the entire field. And he is quite possibly the most brilliant chemist to never be awarded a Nobel Prize, which is an interesting and ultimately tragic story for another day. Let's take a look at his theory of acids and bases. In Lewis theory, bases are electron pair donors and acids are electron pair acceptors. We've now moved from talking about proton donation and acceptance, as we did in Brønsted-Lowry, to talking about electron pairs. This opens up a lot of new possibilities for us. Let's look back at that reaction again. So we said that the lone pair of electrons on the oxide attacks the sulfur dioxide to make the reaction happen. In Lewis theory, this means that the oxide ion is acting as the Lewis base. It's the electron pair donor. Therefore, SO2 is acting as the Lewis acid because it is the electron acceptor. Because we have Lewis acid-base theory now, we can talk about a lot more different types of reactions. Let's take a look at some common Lewis acids and bases. So some common Lewis bases include anions of almost any type. This includes things like hydroxides, the monatomic ions like halogens, Cl- or oxide, S2-. This would also be sulfide, nitride, all of those. or any of the polyatomic ions that you spent time learning about in the fall. It can also be any neutral atom that has a lone pair of electrons, one or more lone pairs. So this includes halogens, fluorine, chlorine, etc., chalcogens, oxygen, sulfur, etc., or the pnictogens, nitrogen or phosphorus. As a matter of fact, some of the most common Lewis bases you will see are oxygen or nitrogen, and this is because they have these lone pairs of electrons that are hanging out and can go ahead and be donated to something. In organic chemistry next year, you'll call these nucleophiles. And they're called nucleophiles because you have this pair of electrons that is seeking the positive charge of a nucleus. So these Lewis bases are going to look for Lewis acids. Common Lewis acids include cations, especially highly charged transition metals. Think aluminum or iron 3+, think chromium 4+, or chromium 6+. That's because these species have a lot of positive charge that they want to balance out by interacting with the negative charge of electrons. You can also find Lewis acidity in atoms that are bound to strongly electronegative atoms. Think HX or CX bonds, where that X is a halogen or oxygen or nitrogen. That's because this X atom is pulling the electron density away from that hydrogen or carbon, making it kind of positively charged, which makes it want to interact with the negative charge of a Lewis base. In organic chemistry next year, these will be called electrophiles because they want to interact with the negative charge of electrons. Lewis acid-base theory also works for Brønsted-Lowry acids and bases. Let's take a look at how. The reaction of ammonia and water reversibly becoming ammonium and hydroxide can be described under both theories. Under Brønsted-Lowry theory, what we've been using, we would say that the water donates a proton to the ammonia. Therefore, ammonia is behaving as a Brønsted-Lowry base because it's accepting a proton, and the water is behaving as a Brønsted-Lowry acid because it is donating a proton. But what about under Lewis theory? Under Lewis theory, we no longer look at the proton, we look at the movements of electrons. Here, we would say that the lone pair of electrons on the ammonia donates to the proton on the water, and that takes that proton away from the water molecule. So we donate the electrons, that pushes the electrons from the hydrogen-oxygen bond back onto the oxygen, giving us our products of ammonium and hydroxide. We would call ammonia the Lewis base because it is donating the pair of electrons, and we would call water the Lewis acid because it is accepting the electrons. Note that in both theories, the base and the acid are the same molecules. We're just describing the mechanism in terms of different things. Under Brønsted-Lowry theory, mechanisms are described by the movements of protons, and under Lewis theory, mechanisms are described by the movement of electrons. By focusing on electrons, which are a feature that all molecules have, rather than on protons, which are things only some molecules have, Lewis theory is a much more versatile theory of acid-base chemistry. I'll see you guys after spring break.